In this video, we'll be looking at how lines intersect in both R2 and R3. So we're going to start off with lines in R2. There are three different orientations that our lines can have. First, you can have them to be not parallel, and therefore they will intersect at a single point. You could also have your lines being coincident, which means they are parallel and just right on top of each other. They're the exact same line, which means you have an infinite number of solutions, and the solutions are every single point on that line. And finally, we can have lines that are parallel and distinct, meaning they never touch, and as a result, we have 0 points of intersection. Now, the way we're going to solve is by using our parametric equations and setting them equal to each other to solve for the parameter that would give us this common point. Now, if we're given the Cartesian equation of the line, then we're just doing substitution or elimination like in grade 10. And another thing, we should always check to see if our lines are parallel before we do any calculation, because if we see they're parallel, then we can just test and see if they're coincident or distinct and get our answer right away instead of setting those parametric equations equal to each other. So, first question, we're going to determine the point of intersection between the lines that and that. So, I'm going to look at the direction vectors. I cannot multiply one by a scalar to get the other. These lines are not parallel. So I'm going to start off by writing the parametric equations for each one. So for line 1, we have x equals 2 plus 5t, and y equals negative 3 plus a single t. For line 2, we have x equals 5 minus 2s, and y equals 1 plus 3s. Now, we're going to start with our x's. X is equal to 2 plus 5t and 5 minus 2s. So let's set them equal to each other. And I'm going to clean this up a little bit by doing a little swapping. So 5t plus 2s equals 3. And I have two variables there, so I need another equation. So I will also set the y's equal to each other. And again, I'm going to clean it up. So bring the 3s over, bring the negative 3 over, and here we are. And now I can just do some nice elimination in this case. So I'm going to multiply this by 5 so I can match the coefficients of the t's. This one I'm just going to copy paste. And now I'm going to subtract my lines to eliminate the t's. Then I have 2 minus negative 15 and 3 minus 20. Now if we divide both sides by 17, we get s equals negative 1. And now I'm just going to sub that in here. So that's t plus 3 equals 4, and t equals 1. So in reality, I only needed to solve for one of my parameters, because the minute I got s equals negative 1, I could plug that into line 2 and get the coordinate, but I'm doing both just to check my answer. So in line 1, I would have 2 minus 3 plus our t, so t is 1, times the direction vector. And that would give me 2 plus 5 is 7, negative 3 plus 1 is negative 2. So I think that's the point of intersection, but I'm just going to double check with line 2. Just a nice way to be confident in your answer. So 5, 1, and s is negative 1, so minus negative 2, 3. 5 minus negative 2 is 7. 1 minus 3 is negative 2. Yep, they're the same thing. So therefore, the point of intersection is 7, negative 2. And there we are. A different way to find the point of intersection of two lines in R2. Let's see R3. Now we have one extra orientation for R3. We still have intersection at a point. We still have coincident lines. We still have parallel and distinct. But we can also have skewed lines. These are lines that are not parallel, but because you have this three-dimensional space, they might not intersect. And the way we're going to differentiate between intersecting and not intersecting, but not being parallel, is with a check at the end, because we won't know until the very end if there actually is a point of intersection or there isn't. But in terms of coincident or parallel and distinct, we're going to check the direction vectors. So, determine the points of intersection, if any, between each pair of lines. So I'm going to start off by looking at my direction vectors here. I cannot write one as a scalar multiple of the other, so these are not parallel. And I'll just make a little note here. So direction vector 1 does not equal k times direction vector 2. So we might have an intersection or they might be skewed lines. But we're going to start the exact same way as in R2 by listing our parametric equations. So 0 plus t, 1 minus t, 2 plus 2t. Negative 3 plus 0s, well that's nice. 4 plus s, negative 4 plus 2s. Now, we have two unknowns, but we're going to have three different equations. So your third equation is going to be your checking method, and that's going to be the check that tells you, is there actually a point of intersection or are the lines skewed? So I'm going to use the x and y parametric equations to solve this, and z will just be for my check. So I'm going to set the x's equal to each other. So t equals negative 3. Well, that's fantastic because now we know our t parameter right away. And I'll set my y's. 1 minus t equals 4 plus s. But we know t is negative 3. And I'll also bring the 4 over. So that's 1 plus 3, which is 4, and 4 minus 4 is 0. Okay. And now I can either sub these into the individual lines to see if they match, or because I know these work on x and y, I can just check the z components. So that's what I'm going to do. So I'm going to put z1, 2 plus 2 times negative 3, that's 2 minus 6 is negative 4. And then for line 2, negative 4 plus 2 times 0, negative 4. They match. There is a point of intersection here. And we know the z component is going to be negative 4. And I'm just going to sub into line 2 because s equals 0 is so much easier. If s is 0, our point is just going to be negative 3, 4, negative 4. Because then it's going to be plus 0 times the direction vector. Therefore, point of intersection is negative 3, 4, negative 4. And make sure you write your point of intersection as a coordinate, not as a vector. Because remember, right here, that is a vector starting from the origin and going to that point of intersection. And again, you could also do a check, like a second check, by subbing in negative 3 in for t for L1 to make sure you get the same coordinate. But you can either check on the z equation because we have that, or check in the actual lines. Your choice. And I'll check the other way in a different example so you can see both. All right, second example. here are our lines. For line 1, our R naught is actually the origin because there's nothing there. So 0, 0, 0 plus t times the direction vector. And I'm going to start off by looking at the direction vector here. So if I look at them, well, it looks like I can multiply 0, -1, and 2 by -3 to get 0, 3, and -6. So the lines are parallel. So maybe we have 0 points of intersection, or we have an infinite number of points of intersection. So I'm going to check and see, is this coordinate on line 1? Because if it is, they're coincident. If it's not, then they're distinct. So the parametric equations for line 1 is just 0. So 0 equals 0, okay. Then y is -6 on line 2. The parametric equation of line 1 is -t. So t equals 6. Z for line 2 is 12, and we're going to set that equal to the parametric equation of line 1, which is 2t. And we get t equals 6. Well, that means that the lines are coincident. So they all match. Therefore, the lines are coincident. There are an infinite number of solutions. And to clarify, I'm going to say any point on, and I can pick either equation because the equations represent the same line. So any point on this is a point of intersection. And there we are. Now, let's say you didn't check the direction vectors first and you just went straight to solving. What would have happened? Because it's good to see that situation as well. So I'm going to write my parametric equations. X equals 0, y equals -t, z equals 2t, x equals 0 again, y equals -6 plus 3s, and z equals 12 minus 6s. So let's set these equations equal to each other and see what happens. Well, x equals 0 and x equals 0, nothing to do there. So -t equals -6 plus 3s, and 2t equals 12 minus 6s. Because I don't have any extra constants, I'm just going to do elimination from this setup. I'm not going to rearrange it. I'm just going to double the first one. So that I have -2t equals -12 plus 6s. And you might already notice things are matching quite a bit. So add the lines. And when I do that, I get 0 equals 0 and 0. And that's your clue. Getting that true statement, 0 equals 0, that's your clue that you have an infinite number of solutions. And then when you see that, you would say, oh my gosh, the lines must have been coincident. And then you can go back, check L1 and L2, and verify that. So there we are. Okay, next example. Again, I'm going to check my direction vectors first. And it looks like I can take 1, -2, 1, and multiply it by -2 to get the second direction vector. So again, we have parallel lines, but are they coincident or not? So I'm going to check, is this on line 2? So my parametric equation for line 2 is 0 minus 2s, and I'm going to set that equal to the x on the point, and I get 1 for s. The y parametric equation on L2 is 2 plus 4s. I'm going to set that equal to 3. 4s equals 1, s equals 1/4. Those are already different. So I know the lines are parallel and distinct. there is no point of intersection. Now, if I were actually to do the solving, because I neglected to look at my direction vectors, then when I did substitution or elimination, I would have ended up with a incorrect statement. For example, 5 equals 0. And that would be my clue that there is no point of intersection, there is no solution. All right, last example. So I'm going to start off by looking at the direction vectors. They cannot be written. So I'll just write m1 times k does not equal m2. So it's not parallel. So maybe we have a single point of intersection or our lines are skewed. So I'm going to start with those parametric equations. X equals -1 plus 0t. Y equals 3 plus 4t. Z equals 6 plus 5t. And for line 2, x equals 4 minus s. Y equals 17 plus 2s. And z equals 30 plus 5s. And again, I'm going to pick the two equations I want to deal with. I'm just going to deal with x and y, and I'll use z for my check. Or I can use z for my check, or I can just use the full-on equations of L1 and L2 for my check, and I'll show it this way this time. So I'm going to set my x's equal to each other. -1 equals 4 minus s. And actually this is great because I can solve for s right away, which isn't always going to happen, but it did this time. S equals 5. I'm going to set my y parametric equations equal to each other. And we know s is 5, so I'm going to go ahead and sub that in. So we have 17 plus 10 is 27, and when I bring the 3 over, 27 minus 3 is 24, and I get 6 for t. So, like I said before, I can check in here to see if the z's match, but I'll show you this time checking using the actual line equations. So -1, 3, 6 plus 6 times the direction vector. That would be -1 plus 6 times 0, 3 plus 6 times 4, so 3 plus 24, 6 plus 6 times 50, so 6 plus 30. There we are. Now I'll test with line 2. So what we're actually testing here is what the point of intersection would be with these parameters that we solved for. If it's actually a point of intersection, we should get the exact same values. So 4 plus 5 times -1, so 4 minus 5, that matches. 17 plus 5 times 2, so 17 plus 10, that matches. And we expect x and y to match because we use the x and y equations to solve for these parameters. The only one we're not sure about is z. So 30 plus 5 times -5, so 30 minus 25, that's 5. Well, here we are. Those are different. These must be skewed lines. And that's why I said in the first example, you could also just check on your z components, because that's the only thing that's going to be different. X and y, because I use them to solve, will match. But there we are. Therefore, no POY because the lines are skewed. And that's it for our points of intersection of lines in both R2 and R3. And just a reminder, your first step should be checking for those direction vectors before you go on to actually solving, because it can save you some time.